Just testing. I'll start in like 2 minutes. Just want to make sure that the audio and everything is working. I think it's good now. Okay, so we'll start now. Starting with sets. So the introduction says that the concept of set serves as a fundamental part of the present day mathematics. Today, this concept is being used in almost every branch of mathematics. Sets are used to define the concepts of relations and functions. That's the topic of the next chapter, relations and functions. So you can already see that they're kind of connected. The study of geometry, sequences, probability, etc., all require the knowledge of sets. So this is just saying that it's important, but it doesn't really matter. This is some more historical stuff. It was developed by German mathematician George Cantor. Not sure how to say that. He first encountered sets while working on problems of trigonometric series, and then in this chapter they're going to discuss some basic definitions. So there's nothing super important here. It's just kind of introducing you to what sets are and how they're used. Now this is going to give you some practical examples, right? In everyday life, we often speak of collections of objects of a particular kind, such as a pack of cards, a crowd of people, a cricket team and its players, etc. In mathematics also, we come across collections, for example, of natural numbers, points, prime numbers, etc. More especially, we examine the following collections. So odd natural numbers less than 10, so that will be 1, 3, 5, 7, and 9. The rivers of India, right? It's a list of different elements. The vowels in the English alphabet, so that these ones, some people say Y is also a vowel. Various kinds of triangles like isosceles, scalene, equilateral. The prime factors of 210, so that's just 2, 3, 5, and 7. The solutions of this equation, right? If you factor it, you'll see that the solutions are 2 and 3. So it's the same thing. The solution of this equation for x would be 2 and 3. You can also write this as just 2 and 3. Each of the above examples is a well-defined collection of objects in the sense that we can definitely decide whether a given particular object belongs to a given collection or not. So this, you shouldn't just have like the rivers of India, right? You know if a river belongs, if you just hear the name of a river, you know that it's either a river of India or it's not a river of India, right? And so you know whether to put it in the set, whether it belongs to the set or whether it doesn't. So it should be well defined. That you have to have some sort of definition that makes sense. So they're just saying, for example, we can say that the river Nile does not belong to the collection of India. On the other hand, the Ganga River does belong to the collection. These are some common sets that you'll come across. So R plus with a plus on top is positive real numbers. R is just real numbers. If you had R minus, that would probably be the negative real numbers, right? Q, same thing with all the rational. So okay, Q is all the rational numbers. So Q plus will be all the positive rational numbers. Z is all the integers. So Z plus is going to be the set of positive integers. And then that's basically so Z plus, the set of positive integers is basically the same thing as the natural numbers, depending on if you include 0 as a natural number or not, right? If you include 0 as part of n, the set of natural numbers, then it won't be the same thing. And then these are just common symbols. So they're pretty logical. Q is my Z, I think, comes from the German word for integers. N is obviously natural numbers. R is real numbers, so those make sense. But Z and Q are maybe a little tricky, so let's practice those a little bit. The symbols for the special sets given above will be referred to throughout this text. Again, the collection of 5 most renowned mathematicians of the world is not well defined because the criterion for determining a mathematician as most renowned may vary from person to person. It's not well defined, right? It's not going to be the same for everyone. So a set is the opposite of that. It's a well defined collection of objects. And the things within a set, you can call them objects, elements, or members. They're all the same thing: objects, elements, and members. They're usually denoted by capital letters like A, B, C, etc. And the members or the elements of a set are with small letters. So A, B, C, all lowercase. If A is an element of set A, it belongs to A, right? And so you show it with this epsilon symbol. It belongs to it, right? It's like kind of like a prong or a pitchfork. So you, if A is part of the set, if small a is part of the set big A, you write it like this. If you're not an element of a set, you write it this way. You put a line through it, right? Just like with not equals, you put a line through it. With not with doesn't belong to, you put a slash through it. So this is just a quick example of that. A would belong to V because the vowel A, um, because A is a vowel and it belongs to a list of vowels, but B is a consonant, so it does not, right? So same thing. There are two methods of representing a set. Now this is where it kind of gets a bit interesting. You can have a roster or tabular form where you just list out everything, right? And so to do that, you put curly brackets and then you put each of the elements and separate them with commas, right? So 2, comma 4, comma 6. You don't put a comma after the last one. It's like if you're listing a list of items like for a grocery list, milk, bread, bananas, right? You put milk, comma, bread, comma, bananas. So that's roster or tabular form. So you can list it out. You basically just list out everything, right? The order does not matter over here. So you can, instead of writing out this long thing, 1, 2, 3, and then 6, 7, 14, 20, or 42, you can change up the order a little bit. You can change it up completely. You can put the opposite order. You can shuffle them randomly, but it's the same thing because you've got the same members within you. The set of all vowels, and then yeah, the other one is set builder form. We'll get to that after this. The set of all vowels is A, E, I, O, U. The set of odd natural numbers is written as 1, 3, 5, and then you put dots to show that it goes on forever because the natural numbers go forever. So the odd natural numbers will also go on forever, like 1,000,001, 1,000,003, 1,000,005. So you obviously can't list them all out, so you just put these dots instead. You usually don't repeat elements. So if you're writing out the elements in school, obviously S, C, H, O, and L are all there, but they're two O's, so you don't need to write them out twice. You can just write them out once, and that's sufficient. In set builder form, all the elements of a set possess a single common property which is not possessed by any element outside the set. For example, in the set A, E, I, O, U, all the elements possess a common property, namely each of them is a vowel in the English alphabet and no other letters possess this property. Denoting the set by V, we write V equals, and then in the same curly brackets, you put X and then you put a colon or a line like this, a vertical line, and then you define it. You provide the definition that is, remember, if you go back to the definition of this, it's a well-defined collection of objects. So you give the good definition here, right? The well-defined comes through over here. This is how it's well-defined. You don't have to use X. You can also write any other letter, right? It may be observed that we describe the element of the set by using a symbol X. Any other symbol like these could also be used, which is followed by a colon. After the colon, we write the characteristic property or the definition possessed by the elements of the set, and then enclose the whole description within braces. The above description of the set V is read as the set of all X. So the set of all X. This colon means such that. So this colon is such that X is a vowel in the English alphabet. In this description, the braces stand for the set of all the colons answers such that, right? So if you did this over here, it would be A is equal to the set of all X such that X is a natural number and 3 is less than X is less than 10. Or instead of saying 3 is less than X is less than 10, you can say X lies between 3 and 10. Hence, the numbers 4, 5, 6, 7, 8, and 9 are all the elements of the set A. If you note the sets described in A, B, and C above in roster form, then A, B, and C can also be represented in set builder form. So this is one example, Y set, the set of Y such that Y is a vowel in the English alphabet, and so on, right? These are just different ways of converting between the two. So if you wanted to write this in roster form, you'd find the roots first. You can factor this as x minus 1 times x plus 2. So you're going to have x equals 1 and negative 2, and then you put them in roster form. You just list them out. What about this one? So you'd have 1, 2, 3, 4, 5, and 6. So you just put that into the set over here, right? Easy enough. Write this set in set builder form. 1, 4, 9. Okay, what does this look like? It's just a natural number squared. So you would just write this. And you have to mention that it's a natural number, right? That n over here is a natural number. So you put where n belongs to the set of natural numbers. So this is kind of going back to what they mentioned earlier about these special sets, right? So sometimes you do have to refer to these. And that's exactly what they're doing here. What about this? Well, it's 1 over 2, 2 over 3, 3 over 4. So it's n over n plus 1. So you see that over here as well. but there are limits on n, right? N can't be 100. That's not part of this. So you say n goes from 1 to 6, right? And you just write it like that. You can, instead of saying n is a natural number, you can say n belongs to this. So you can do this here as well. It's up to you. You don't have to, this is just a little shorter, a little bit more mathematical, but this is the exact same thing. Okay, next example. Match each of the sets on the left described in the roster form with the same set on the right described in set builder form. What about this one? Let's start with B. If x squared minus 9 is 0, x is equal to either plus minus 3. So 4 and B will go together. X is a letter of the word principal, so obviously I and D, 1 and D. X plus 1 equals 1, so x is 0. So 2 and C, and then obviously by process of elimination, 3 and A. Exercise 1.1. Which of the following are sets? Um, okay, so remember, it just has to have a well-defined thing. So yeah, it's January, June, July. I think that's it, right? So it's just because there are 12 months of the year. You know what letters they start with. So see which ones start with J and put them in. That's it. 10 most talented writers. This is not well defined because people have different interpretations. They might not agree. Best cricket batsman, same thing. You don't know for sure. Collection of all boys in your class. If you know someone, well, okay, well, this one's a little bit trickier, I guess. But I mean, I think the intention of the question is that yes, you know if someone's a boy or a girl. Um, and if it's a boy, well, if they are a boy and they're in your class, then they belong to the set, right? Otherwise, they don't. The collection of all natural numbers less than 100, same thing. It'll be 1 through 99. Again, this is objective, it's well defined, so that's correct. Same thing with 7, same thing with 8. Most dangerous, again, this is not, there's no scale of danger for animals, not that I know of, so it's going to be more subjective. It's based on your opinion, and everyone needn't have the same opinion. So it's not well defined, right? It's not going to be the same. Other people might have different sets. Okay, now we're just checking to see if, okay, so does 5 belong to the set A? Yes, it does. So we put this one. 8 does not, so we'd use this one. 0 does not, so we'd use this one again. 4 does belong, 2 does belong, and 10 does not belong. So just based on whether 5, 8, 0 belong to the set A, you either use the epsilon or the epsilon with a slash. Write the following sets in roster form. So, well, okay, it's pretty simple, right? Let's skip the first few. The set of all letters in the word better, so you put B, E, T, R, right? You don't need to put E twice, you don't need to put T twice. So B, E, T, R, that's it. Write the following sets in the set builder form. So just find the pattern and then write it. Like this would be 5 to the n, where n belongs to natural numbers and n goes from 1 to 4, right? That's it. Same thing here. These are squares. So you just say it's x equals n squared, where n belongs to the natural numbers from 1 through 10, right? Something like that. Okay, list all the elements. What would you have? You'd have Loya. You don't need to write L twice again because it's loyal has L twice. You only need it once. X is a consonant in the English alphabet which precedes K. So you'd have B, C, D, F, G, H, J, right? So logical and simple enough. This is very similar to the other question we did, right? So math, this would go with this one. 1, 3, 5, 7, 9, these are all odd numbers, so I think it would be this one. 2 and 3, so 2 and C, 1 and, oh, wait, no, sorry, 1 and A, and then, no, 2 and A, and then 1 and C. Just look at the definitions and match them. Now we move on to something a little bit more interesting, maybe. This is called the empty set. So consider set A, where X is a student of X such that the set of X such that X is a student of class 11 presently studying in a school, right? And there's going to be a finite number of students because it's like a real world thing. They're not infinite students, they're not infinite people. We can now write another set as follows. Okay, so this is what they're getting at. So X is going to be a student who's presently studying in both classes 10 and 11. That's impossible, right? A person can't be in both. So there isn't going to be anything within the set. B is going to be the empty set. Okay, and this is the main definition that we get to. A set which does not contain any element is called the empty set, or the null set, or the void set. So again, all three of these mean the exact same thing. According to this definition, B is an empty set, while A is not an empty set, because this will be lots of different students, and B will have no one in it, right? And there are a few different ways of writing the empty set. You can put phi or phi, or you can just put a little empty set, nothing inside. Okay, like look at this one. There's no natural number between 1 and 2, so that set is going to be empty. There's no rational number that satisfies x squared minus 2 equals 0, so that's empty. There's no even prime number greater than 2, so this is also going to be empty. And if x squared equals 4, x is equal to negative or positive 2, neither of which are odd, neither of which is odd, and so D is also the empty set. So that's a pretty quick section. Hopefully that made sense. Let's now talk a little bit about finite and infinite sets and infinite sets. So over here, A has 5 elements, B has A, B, C, D, E, G, that's 6 elements, and C has men living presently in different parts of the world. You can probably estimate this. We might not know the exact answer, but we know that not going to be um, it's not going to be infinite because there aren't infinite men living, right? It might be a very, very big number. It could be like several billion, probably like 4.5 billion people, but that's still a finite number, right? So none of these are all finite sets. They have a finite number of elements. By the number of elements of a set S, we mean the number of distinct elements of a set S, right? So that's another important thing. All men are distinct, right? They might have the same name, but they're different people. So that's why if everyone were the same, then that would just be one, right? The number of elements of a set. And the way you write it is by n of S. So just like with the function, it's n bracket S bracket. And if it's a natural number, so if the total number of elements is 1, 2, 3, something like that, then it's a non-empty, right? Non-empty means that it's not zero, and then finite is that it's an actual number. It's not infinite. Consider the set of natural numbers. We see that the number of elements of this set is not finite since there are an infinite number of natural numbers. So it's an infinite set, infinite set. A set which is empty or consists of a definite number of elements is called finite. If it's not that, then it's called infinite, right? They're just opposites. They're complements of one another. So these are some examples. The days of the week, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, that's finite. The number of solutions of this, there are only 2 solutions, plus minus 4. Let G be the set of points on a line. There are infinite points on a line, right? You can, like if this is a line, there's this point, this point, this point, this point, every point in between, so that's infinite. When we represent a set in roster form, we write all the elements of a set within braces. If you got an infinite set, of course you can't do that, right? Because they're infinite things. You can't fit those within 2 brackets. And so you represent some infinite set in the roster form by writing on a few elements, and then you'll just put dots after that. So we saw an example of that with 1, 2, 3, dot, 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 I think. Where was it? Yeah, this one, 1, 2, 3, dot, dot. So you can see the pattern, but obviously you aren't going to write down all the squares, right? So you'll only write a few, and you'll make the pattern clear, which clearly indicate the structure of the set followed or preceded by 3 dots. For example, 1, 2, 3, dot, 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 1, 3, 5, so that's all natural numbers. 1, 3, 5, 7 is all odd natural numbers, and this is all integers, right? Positive and negative. All of the sets are infinite. All infinite sets cannot be described in the roster form. The set of real numbers, you can't do that, for example, right? Because there's no particular pattern. There's no way to show. There's no pattern that they follow. It's literally all numbers, right? So there's no pattern there. Try it out for yourself and you'll see that as well. Okay, let's look at this. There are 2 roots to this. So this is going to be finite. This is going to be finite. This is going to be finite. This is going to be infinite. They're infinite primes, so it's going to be infinite. And this is going to be infinite. Given this, okay, yeah, finite, 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 infinite, infinite. Yep. Equal sets. How can we see if 2 sets are equal? Just like in algebra, we can, or with algebra, algebraic expressions, matrices, vectors, all those things we can check for equality. And you can do basically the same thing even with sets. To check if 2 sets are equal, all the elements have to be the same. So all the elements of A have to be in B. All the elements of B have to be in A. There shouldn't be, everything should be in overlap. Okay, so you write A equals B if they have the exact same set of elements. Otherwise, the sets are said to be unequal, and you write A is not equal to B. So the same idea, you put an equal sign or an equal sign with a slash. Let's consider a few examples. 1, 2, 3, 4. 1, 2, 3, 4. Different order, but the same stuff. So A equals B. Prime numbers less than 6. Prime factors of 30. If you list it out, A will be 2, 3, and 5, and P will also be 2, 3, and 5. So yeah, again, they are the same. They are the same set. A set does not change if one or more elements of the set are repeated. So 1, 2, 3, and then 1, 2, 2, 3, 3 will be the same exact thing. So repeating things doesn't really change anything. That's why it's just superfluous and redundant to actually repeat anything. Hi, Ankush. Right? If you have a set with just one in it, you can write one, or you can write 1 comma 1 comma 1 forever. And but there's obviously no benefit to doing that because it doesn't change anything about the set. Find the pairs of equal sets, if any, and give reasons. So this has nothing in it. This has 0 in it. That is something, right? So this is not the empty set. What about this? Here x is equal to 5. Um, there's nothing in this. This is the null set. This would have the roots 5 and -3. So this would match with this one. So C and E. Yeah, that's it. Example 8. Which of the following pairs of sets are equal? Just where answer. Set of letters in alloy and B the set of letters in loyal. Both of them have L-O-Y-A, L-O-Y-A. That's it. The L's are repeated. So those two would be equal. The second one, n squared is less than 4. Um, so that would be what? 0, 1, and 2. No, -2, -1, 0, 1, 2. And what about the second one? This would just be 1 and 2. So they're not really the same thing. Yeah, they're not the same set. Set of odd natural numbers divisible by 2. If it's odd, it's not going to be divisible by 2, so there's nothing in this. This is a null set. Set of even prime numbers. 2, there is the number 2 that's even and prime. So that's not the null set. X is a natural number. X is less than 5 and greater than 7. That's impossible. So that's a null set again. Point common to any two parallel lines. Okay, it depends. If two lines are the same line and they're I don't know how they're defining it, but if there are two lines like this and there's nothing in common, then they're obviously that's a null set. But if they're the exact same line, then it's an infinite set. So it kind of depends on how you define it, but I think the answer they're looking for is nothing here. It's a null set. This is finite, this is infinite, this is finite. The dot 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 here, like you're starting somewhere, you're ending somewhere. They just aren't showing everything in the middle, but they could if they wanted to. The set of positive integers is greater than 100. This is everything past 100, so that's infinite. Set of prime numbers. So you start at 2, 3, 5, and then you go until 97. So that's fixed. That's finite. Set of lines which are parallel to the x-axis. Um, you'll just have the lines y equals anything except 0. So y can be 1, 2, 3, 4, 0 0.5. Y can be pi, the square root of e, anything, right? So that's going to be infinite. This is only 26 things, so that's finite. Which are a multiple of 5. You'll have literally any multiple of 5. They're infinite multiples of 5. So this is infinite, this is finite. The set of animals living on the earth. There's a fixed number of animals. It might be a huge number, but there's a fixed number of them. So this is finite. This, think about it, right? You can, if you write the equation, it'll be x squared plus y squared equals r squared. R can be anything. And so r squared can be anything, I should say. And so the set of circles, there'll be an infinite set of them. Infinite. In the following, state whether A equals B or not. Yes, in the first one, yes, because it's the same elements. 4, 8, 12, 16, 4, 8, 18, 16. They're not the same thing, so no. 2, 4, 6, 8, 10. X is a positive even integer and x is less than or equal to 10. So 2, 4, yeah, same thing again for 3. So this is, they are equal. X is a multiple of 10, 10, 15. No, well, it would only be 10, 20, 30, and so on. Here you've also got 15, 25, 35. So this would not be true. Are the following pairs of sets equal? Give reasons. 2 and 3, x is the solution of this. No, this is -2 and... Oh no, sorry, wait. No, this is -2 and 3, so they're not the same. X is a letter in the word follow. Um, yeah, so they have the same letters. This just has two L's and two O's, but this also has an L and an O. So these sets would be equal. From the sets given below, select equal sets. Okay, E and G. D and B. I think that's it. Subsets. Now, subsets are kind of similar to members in that it belongs to a set. But instead of saying that an element belongs to a set, you're saying that a set belongs to a set. So let's read through this. A set A is said to be a subset of a set B if every element of A is also an element of B. In other words, A belongs to B, or well, A is a subset of B. Oh, sorry, over here. Consider the sets X equals set of all students in your school, Y is sets of all students in your class. We note that every element of Y is also an element of X, so we say that Y is a subset of X. The fact that Y is a subset of X is expressed in symbols as Y, and then you've got like this long weird fat C. So Y is a subset of X. The symbol is a subset of stands for is a subset of or is contained in. Moving on to the definition, a set A is said to be a subset of a set B if every element of A is also an element of B. So this is going to be true when everything that belongs to A is also belongs to B. And so this in math, when you're dealing with logic or proofs, then you see this, which means or implies. And so you can write it like this. If A belongs to, so if a set, wait 1 second. Oh, okay, okay, I see. So this is true when if something belongs to A, you know that it also belongs to B. That means that everything within A has to belong to B, right? So if this is true, if this condition is true, then this holds, right? So that's one definition. It's a little bit weird to think about, at least to me. Um, but yeah, it makes sense. A is a subset of B. If A is an element of A, implies that A is also an element of B, right? And if this is not the case, if A is not a subset of B, then you just write A is not a subset of B. As simple as that. We may note that for A to be a subset of B, all that is needed is that every element of A is in B. It's also possible that every element of B may or may not be in A. If it so happens that every element of B is also in A, then we shall also have B is a subset of A. But that can only happen when you've got the exact same elements in both of them, right? Because in this case, you have everything in A is in B, everything in B is in A, so they have to be the same thing. And so that implies A equals B. And this is an if and only if. If you know A equals B, then you know that A is a subset of B and B is a subset of A. And if A is a subset of B and B is a subset of A, then you also know that A equals B. So it's either way. You can go from either side to the other. Follows from the above definition that every set A is a subset of itself. And since the empty set phi has no elements, we agree to say, so this is a little bit more like debatable, but people generally agree that phi is a subset of every set. So the set of rational numbers belongs to all the real numbers. This is a typo, real numbers. And so you could write this. If A is a set of all divisors of 56 and B is a set of all prime divisors, and obviously B will be a subset of A, or natural number less than 6, they're equal over here. If A is A, E, I, O, U and B is A, B, C, D, then neither of them are subsets of the other. Let A and B be two sets. Um, yeah, so if they're not equal to each other and A is like has the same stuff as B, and B has everything within A but also extra stuff, then B is a superset of A. So it's basically you've got everything in A and then more. Okay, little side note here. This doesn't really fit in well over here. But if a set A has only one element, we call it a singleton set, and then you write that with just one element inside. Right? It's just a different name. Singleton because it's like single, it's all by itself. Consider the sets of phi. A is 1 and 3, 1, 5 and 9, and then 1, 3, 5, 7, 9. insert these symbols and try to figure it out. So okay, obviously A belongs to everything. No, sorry. Phi belongs to B. A does not belong to P. A does belong to C, and B does belong to C. Let A equal A E I O U. B is A B C D. Neither of them are subset of the other, because you don't have this. Everything within A is not within B. Everything within B is not within A, right? And so you know that that's not the case over here. Okay, let's move on to the next section now. Subsets of the set of real numbers. If we go up here very quickly, the real numbers are the most inclusive, right? These real numbers include all the natural numbers, all the integers, all the rational numbers, and then even things that are irrational, right? So those are the most um, they're the most inclusive set. They're the biggest one. So n, z, and q, the natural numbers, integers, and rational numbers are all subsets of R. And I think that's what this section is going to talk about. So let's go and take a quick look here. As noted in section 1.6, there are many important subsets of the real numbers. We give below the names of some of these subsets. So we already saw this. Natural numbers, integers, rational numbers, and the definition of rational numbers, in case you forgot, it's just that you can write it as, essentially you can write it as some sort of fraction with integer numerators and denominators. Members of Q include -5 because you can write it as -5/1, and anything else that's a fraction. So all of these work. Irrational numbers are denoted by T. So this is less common. That's why they didn't list it up there. But this is basically all the real numbers except for the rational numbers. So root 2, the square root of 2, the square root of 5, pi, e, all of those are irrational. Some of the obvious relationships are, well, okay. So the natural numbers are part of Z, which is a part of Q, which is all the rational numbers. The rational numbers are a subset of the real numbers. The irrational numbers are a subset of the real numbers. The natural numbers are not part or not subset of the irrational numbers. Intervals as subsets of R. So let A and B belong to R, and if A is less than B, then the set of real numbers from A to B is called an open interval, and you write it like this. So the reason it's open interval, what open interval means is that you don't include A or B within the set. All the points between that belong to the open interval, but A and B themselves are not part of it. If you want to include A and B, then you use square brackets and you call it a closed interval, like so. And this is now, so all that's changing here, instead of A is strictly less than Y is less than B, it's A is less than or equal to, and then less than or equal to B. You can also have it half open, half closed. So you can put like a square bracket on one side, so curved bracket on the other side, or vice versa. And these notations provide an alternative way of designing the subsets of a set, designating the subsets of set